let's get started. A few announcements. So midterm is coming up now in 9 days. Not this Thursday, but the week from Thursday. The midterm is probably going to be a mixture of multiple choice questions, maybe some short answer questions, and 1 or 2 long form open questions, like, come up with an algorithm to do something or write a proof of something. There'll be, hold your questions, let me finish, and then if I didn't answer them. Yeah, it will be held in this room at the usual time. It'll be on, paper, good old-fashioned paper type exam. I'll hold a review session, probably not during lecture time. I'll probably schedule it at a separate time, and then I'll record it. So those of you that can't make it will have the recording. And also, if you wanted to ask questions but can't make it, you can just post them on Campus Wire and I can answer them during the review session. Yeah, other things, there will be probably a practice midterm. And in terms of homework, usually homeworks are due on a Thursday. So I'm thinking that homework that's due the next Thursday to give you an extension until like maybe the Tuesday after or something like that. So you have time after the midterm to work on it. I'll give more details later on during the review, but that's what I have now. Any questions? Yeah. Oh, sorry. Yes, the material. So all the material that's going to be on the midterm, we've already covered. So what we start today is not going to be on this first midterm. Yeah. I can't hear you. Yeah, so the material for the midterm is going to be everything before today. So everything today onwards is not going to be on the first midterm. Other questions? And it's a natural breaking point, because we've basically talked so far on, well, divide and conquer was the last thing we talked about, coming up with divide and conquer algorithms. We talked about how to analyze the running time of divide and conquer algorithms via recurrence equations and solving them with Master's theorem and recurrence trees. Yeah, and before that, we looked at proving algorithm correctness and analyzing running time more generally with asymptotic notation. Anyway, I'll go over that a bit more in detail in the review, but now we go into a new area, which are algorithms on graphs. So graphs, chapter 3.1 in your book. We'll go over that today, covers the basic definitions. I assume you guys have seen them in 360 and have worked with them to some extent. So I'm just going to give a review of notation so that we're all on the same page. So a graph, this is, for example, a graph. Okay. This is what's called an undirected graph. And a directed graph will have directions on the edges. So this is a directed graph. These guys are called, well, maybe I shouldn't use vertices. I shouldn't use arrows. So these guys are called vertices or nodes. These guys are called edges or sometimes arcs. Normally a graph is a set of vertices V and edges E, where V is going to be a set. We'll usually refer to the elements of the set using lowercase v, sometimes u, and we'll say v1 through vn, where n is the number of vertices, the size of the vertex set. For edges, we have to separate undirected and directed case. So edges E, so for undirected edge, we think of an E as a set of two elements, X and Y, for X, vertex X, and a vertex Y. And here, importantly, it's a set, meaning there's no order on it. So just two elements, X, Y, Y, X, it doesn't matter. And a directed graph, we think of E as an ordered pair. So the parentheses, remember we've used parentheses to indicate sequences. So here it's a sequence of two elements. Well, like a set, a sequence has an order. So again, X and V are, X and Y are in V, but X, Y is different than, so X, Y is not equal to Y, X. These are different edges, right? So, yeah, like when we talk about graphs, we're gonna be, talking about technical details, algorithms, speed, and so on. But it's important to remember the connection of graphs to real world. Why are they coming up in the real world? Where are they coming from in real life? Do you guys have any example of things that can be modeled as graphs? Have you seen anything? Yeah. Okay, so a road network. In a road network, what would be the edges and what would be the vertices? Yeah, that's how I would do it. So, and here important, well, to summarize the answer is the vertices should be intersections and roads become edges. But you made a good point that it's really a question of modeling real world. You can model the real world in any crazy way you want. It's just a question of, is it useful? Is it useful to model? Is your model useful? For a road network, this is a very natural way to model it. So, that's a good example. Other examples of, by the way, network is often used interchangeably with graph. What are the chances I'm going to spell this correctly? Interchangeably with graphs. Other examples? Yeah. Social networks, it's a good example. What's today? I haven't kept touch. My generation still uses Facebook. What's the social network of choice today? Instagram, I don't know. Nobody is like, do we not even use social networks anymore? Have I fallen that far behind? Yeah. With TikTok. And then TikTok, yeah, I've heard about it. I don't have an account. So can you like become friends with someone or you follow them? How does it work? Okay, so TikTok, how would you model TikTok as a graph? Yeah. So I think you're saying so user becomes a node, and if John follows Jane, then we draw an edge from John node to Jane node. Okay, and is that a directed graph or an undirected graph? TikTok. Directed? Directed. So yeah, so if John follows Jane, it doesn't mean that Jane follows John. It's a directed graph. Is there a social network where it would be better modeled as an undirected graph? Yeah. Is that right? So in LinkedIn, if you're connected, it's a two-way. If LinkedIn, if you're connected to someone, then they're connected to you. Good. So LinkedIn is an undirected network. I think in the previous section, someone said LinkedIn, you follow people, in which case it's a directed network. So it basically depends on what you exactly want to model. Is it a symmetric relationship or is not? So Facebook, for example, is a classic undirected network, would be classically an undirected network because you're friends with someone and it's a symmetric relationship. Other examples? Comments? Yeah. I've never played this, so how does it work? Oh, Oh, I see. So that's interesting. Constellation. So when we draw constellations, it kind of looks like a graph, right? I don't know how Big Dipper goes. Something like this. So that's interesting. But there the edges are kind of man-made. We just draw these things to better visualize the constellation, but I guess there's nothing really physical behind those edges. So that's, yeah, I guess I wouldn't think of that as a graph, even though it looks like a graph. Yeah. Well, gene regulatory networks, that's up my research alley, but I don't know. Can you explain for people that don't know? Yeah, so in the gene regulatory network, I guess there are different ways to do it. You could have one gene, put it very simply, one gene regulates the expression of another gene. So it regulates how much of that other gene is produced. There are things called protein interaction networks. This really comes up in biology quite a bit. So the algorithms that we're going to be talking about, we'll get real technical. We're not going to come back to the application areas, but it's important to understand that there are social implications about the algorithms that we are going to be developing, in the sense of like, now a lot of things are in the news is how social networks regulate speech. So for example, does Twitter ban hate speech, or where does it draw the line, things like that. So think about it. Okay, let's say, great, let's ban hate speech. How do we detect tweets that are considered hate speech? Do you have some poor person sitting in a room going through millions of tweets per day and saying, oh, this is hate, this is not hate. No, right? That doesn't work. There are going to be algorithms that work on the Twitter graph that are processing, that are also working on the text of the tweets and trying to decide whether to flag this as hate speech or not. So you might have algorithms that can do this effectively, or maybe you don't have algorithms that can do this effectively. And this can be a difference between being able to implement the policy or not being able to implement the policy. So let's say everybody agrees that this policy for filtering tweets as hate speech, this is the policy that we want. Okay, and there's like agreement on that. Well, if you can't have some kind of underlying algorithm that can scale, that can help implement that policy, then you can't implement that policy. If you have algorithms, then it can open doors and facilitate things. So there's a lot of social implications, or just implications to real world, not just the technical, not just the world of computers and networks or road networks or biology, but really to things that every day in our lives we interact with. Okay. So having said that, now let's get technical. So let's go back to the undirected versus directed graph. One thing I want to say is that an undirected graph can be viewed as a directed graph where edges are always come in pairs. One in each direction. So like we had this example. We could draw this as a directed graph by doubling every edge. It's the same in the sense of all the paths are there that exist in the left graph, they exist in the right graph. And so maybe it's a good time to also define what is a path. So path is a sequence of vertices such that consecutive vertices connected by an edge. So let's put V1 here. Let's call them V1, V2, V3, V4. For example, then the yellow, this would be a path. So P equals to V1, V2, V3, V4 is a path. On the other hand, P equals to V1, V2, V4 is not a path. Right? V1, V2, V4, there's no connection between V2 and V4, so it's not a path. Yeah. No, so V1 to V2 is a path. in fact, sometimes we think of just V1 as a path, just the smallest path possible is just the vertex. But V1, V2 is also a path. In the directed case, let's draw a more interesting directed graph. V1, V2, V3. Here, P, let's say V2, V3, V1, that's a path. So V2, V3, V1 is a path. But P equals to V2, V3, V4 is not a path. So this guy, V1, V2, V4 is not a path. See why? Because there's no edge from V3 to V4. Right? There's V3, V4, and the path, if it's a path, then has to be an edge from V3 to V4. But there's no edge from V3 to V4. Right? There's an edge from V4 to V3, but that's not what we need. So besides path, there are also cycles. So a cycle is a path that starts and ends in the same vertex. We haven't so far had an example of a cycle, but you could come up with one here. For example, P equals to V3, V1, V2 is a cycle. V3, V1, V2. And finally, again, V3 is a cycle. So V3 to V1 to V2 to V3. That's a cycle. So that's the review of just basic graph definitions. Any questions? Okay, so next, how do we analyze runtime or space of graph algorithms? Well, we already talked about how to analyze in terms of number of steps taken by algorithm as a function of n, where n is the input size. But what is going to be our n here? It's a little bit trickier than say sorting. So we're going to use n to denote the number of vertices. We saw that. We're going to also use m to denote the number of edges. And we're going to think about both of these quantities when we analyze our running time or space usage. Let me ask this, true or false? Number of edges is more than the number of vertices. How many of you think this is true? How many of you think this is false? For those of you that think it's false, do you have an example of where it's false? Yeah. Okay, very good. So even this example, you have one edge, two vertices. So what if I put minus plus 1 here? Is this true or false? How many of you think this is still false? How many of you think that this is now true? So those of you that think it's false, what's a counterexample? It is false. Yeah. You can have a graph with only vertices and no edges. This is a graph. Or you could have like one edge. Okay, so in this graph, you can have as many vertices as you want, and you can still have no edges or one edge. So this is false. This is E can be less than V. Okay. What about how big can E be? Can E be? Do you guys have an example where E is, let's say, big theta of V? Graph. Yeah. Well, that's not in that case, E is not theta of V. Yeah. Two vertices. But where do you draw? You can only have one edge between a single pair. Yeah. And this acyclic graph? Oh, so just a cycle like this. Yeah, that's good. So there, the number of edges is exactly the number of vertices. Other examples? Yeah. A square. Yeah. Same idea where the cycle of length 4. About a tree. Have you guys have seen trees? Like, let's look at this binary tree. How many vertices are there? 7, right? How many edges? 6. Is that a coincidence? What if I draw another level? How many vertices did I add? 8. So, okay, let's become 7 plus 8 becomes 15. How many edges did I add? 8. So 8 plus 6, 14. Space to do another example, but if I, another level, but if I do another level, I'm going to add 16 vertices and 16 edges. And so you'll still have this relationship that n is equal to m plus 1. In fact, any tree will have the number of edges being theta proportional to the number of vertices. Okay, what about this? A graph where the number of edges is squared of the number of vertices. Any examples of that? Actually, we had an earlier, someone brought this up. A complete graph. A complete graph has all pairs of vertices connected. So for example, this is a complete graph of 3 vertices. That's not very interesting. That looks just like a cycle. But here's a complete graph on 4 vertices. Put everything, connect everything that's possible. All right. What about 5 vertices? We connect everything that's possible. In a complete graph, what if n is the number of vertices, how many edges do you have? Well, you have n choose 2 edges. N choose 2 because you choose something for it's the definition of n choose 2, right? You choose 2 elements. How many ways are there to choose 2 elements from out of an n element set? And here you have n vertices, and choosing 2 vertices is exactly putting an edge in there. So how many different ways can you put an edge? N choose 2. Choose 2, you guys remember what's the formula for n choose 2? N times, no, n choose 2, yeah. And what's that? Which is 2, yeah. And this is, in terms of asymptotics, n squared. For the square one, the number of edges is, you mean for this one? It should be precisely n times n minus 2 over 2. So let's see. So here n equals to 4, m n choose 2 equals to n over n times n minus 1 over 2, which is 4 times 3 over 2, which is 6. And we have 1, 2, 3, 4, 5, 6. Checks out. So there are these kinds of, so that's what kind of makes this analysis with graphs a little more complicated than we saw with, for example, sorting, is that you have these 2 parameters of the input size, n and m, and it's not, their relationship is not clear. I mean, m could range from being a constant, the number of edges could range from being a constant to being number of vertices squared. And that creates, that means it's not always clear which algorithm is better. So for example, alg1 might run in theta n log n time. For example, it could somehow sort the vertices, right? That's algorithm that would take something like this. And alg2, let's say it does some linear scan and does something for the edges. So it's theta m. Well, which one is faster? Or let's say even this are algorithms for the same problem. Which one would you choose? In sorting, yeah, if you have n squared algorithm and n log n algorithm, you just say, well, the n log n is clearly asymptotically better. Here, it depends, right? And in order to really say how it depends, we have this notion of sparse graphs and dense graphs. So sparse graph is a graph, sparse graph has few edges. So for example, yeah, m equals to big O of n. For example, a tree, like we saw before. or that isolated, or that graph with isolated vertices. That's also a sparse graph. In a dense graph has many edges. In that case, we would write M is theta n squared. For example, the complete graph. When we look at these two algorithms now, we can say one is better when the graph is sparse, one is better than when the graph is dense. So who thinks, let's say I have a dense graph. Who would choose algorithm 1? And who would choose algorithm 2? I guess no one else is running the algorithm. All right, let's try again. If you have a dense graph, then and you don't run that and you don't choose any algorithm, then you automatically lose. Or so who goes for that? Good. So then your other remaining choices is with a dense graph to choose algorithm 1 or algorithm 1, don't be shy. Don't be shy. Okay. And algorithm 2, don't be shy. Don't be shy. Okay, so let's see. If M is theta n squared, then we plug in here, if dense graph, it's theta n log n versus, so this is alg 1, versus the alg 2 theta m, m is now n squared. Okay, so this now looks to me like algorithm 2 is better. Sorry, algorithm 1 is better. Algorithm 1 is faster. N log n is faster than n squared. Something you should be pretty comfortable with by now. N log n is much faster than n squared. And so if in a dense graph, you prefer algorithm 1. In a sparse graph, so algorithm 1 is n log n, alg 1. And algorithm 2, well, m is big O of n. So we can write down that if it's theta m and m is big O of n, that becomes big O of n. Now, alg 2 is faster. So this is really the take-home message is that with graphs, we keep the m, we say things in terms of m and n, keep them separate in our analysis, because then we'll be able to tell, if we know, for example, our graph is sparse, we'll be able to know which algorithm is faster. Or if we know our graph is dense, we'll be able to choose the right algorithm. By the way, what's an example of a dense graph like this? Well, a complete graph is an extreme example. You really have every edge. But even, let's say, a dense graph where between any two nodes, let's say the chance that there's an edge is like 1%, that's still a dense graph. That's still a dense graph. The number of edges will be 10% of n squared, which is still theta n squared. Yeah. Yeah, let me write it down. So a graph consider a graph where we put an edge between two nodes with some probability p. P, think of like 10%, 1%, for example. P equals to 1%. This graph is still dense. The number of edges in this graph is going to be, on average, um, 0.01 times n choose 2. Bless you. All right, so n choose 2, remember, was there possible n choose 2 edges. 0.01 n minus 1 over 2. This is still theta n squared. So this is a dense graph. Even though this P might be small, 1%, it's still in the end a dense graph. So any examples of dense graphs, how dense graphs might arise in real life? Yeah. So, but in that, make it specific. So in that example, what is your graph? What is the vertex and what is the edge? Okay, so let me make it into a slightly simpler example. If you have a graph, just think about airline where I can fly from one place to another. I can make connections, whatever. So there exists a route. And the vertices are the airports, and an edge connects to airports if I can somehow get from there to there on a commercial airplane. Probably this graph it's probably nearly complete. I mean, I imagine in today's world, I can probably get to any airport. I may have to pay a lot. I may have to make a lot of connections. I'll probably lose my luggage. Anyway, but it's possible, right? So that could be a complete graph. Other examples? Well, yeah. So the internet, but be specific. What would be a vertex and what would be an edge? So if your vertices are websites, and well, let me make this example of a hyperlink graph. Your vertices are websites, and there's an edge if one website directly references to the other. I guess it's not exactly what you meant. So this graph, it's not clear to me. It may be a sparse graph. Someone in the previous lecture actually said that the studies show that this graph is sparse because most of the internet of the web pages are not linking to a lot of other web pages. So it makes sense that it's sparse. What about, let's say, Facebook? Do you guys still have, people have Facebook accounts? No? Instagram? So, okay, let's say Instagram. Is Instagram network, do you think it's a sparse or a dense network? So that graph where a user is a vertex and an edge connects to people of their, I guess it's a directed graph. So an edge connects X to Y if X follows Y. Do you guys think that's a dense graph or a sparse graph? So it's an interesting point. So if you could have a person in there that is following a lot of others, but in terms of the whole graph, if you look at the whole graph, then the we call it the neighborhoods of any vertex are usually small. Like you may follow 100 people, for example, but there are millions of users in Instagram. So that whole network is actually a sparse network. But what if I take the Instagram network just limited to people in this class? Now it should have more density, right? It should have a more percentage of edges being present because you guys, you're in the same class, you're in the same major, you're all at Penn State, you might have other connections. So it's you have more follows than sort of average people that are not connected. What if I take a group of friends, like a group of 10 friends, and look at their Instagram network? That should hopefully be a dense graph. So they'll be following, tend to be following each other. Otherwise, it'd be a weird friends group. All right, other questions about sparsity and density? So let's talk about representation of graphs. When we talked about arrays, we didn't have to talk about representation because literally you store it like a sequence of numbers, you would store it as an array for sorting, for example. With graphs, it's not so simple. So there are at least two popular representations that can be used. And we'll cover those. The first is called an adjacency matrix. This is an n by n matrix, A, where Aij, so the cell corresponding to row I and column J, is 1 if there exists an edge from Vi to Vj and 0 otherwise. So let's say V1, V2, that's our graph V3, and V4. Let's say it looks like this. Well, the matrix A will be having 4 columns, 4 rows. The columns correspond to V1, V2, V3, and V4. The rows, the same. And now we put a 1 if there's an edge. For example, V1 to V1, there's no edge. V1 to V2, there's an edge. V1 to V3, there's no edge. Right? There's an edge in the opposite direction, but not from V1 to V3. There's no edge from V1 to V4. From V2, there's no edge to V1. There's no edge to V2. There is an edge to V3, and there's no edge to V4. From V3, there's an edge to V1 and nowhere else. And from V4, there's an edge to V3, nowhere else. Okay. For an undirected graph, so that was a directed graph, but for an undirected graph, A is symmetric. So let's look at a undirected graph, V1. Let's do the same one, but without directions. Here, V1, V2, V3, V4. V1 is connected now to V2 and V3. But symmetric, yeah, and the rest are 0. V2 is connected to V1 and V3, and the rest are 0. V3 is connected to V1 and V2, and the rest are 0. And V4 is connected to V3, and the rest are 0. Notice that the matrix is symmetric. So if you flip it, around here, then you have the same value. So V1, V2 is 1 if and only V2, V1 is 1. And that just comes from the way we construct it. Anyway, okay, so that's the adjacency matrix. The space used by this matrix, well, it's pretty clear because it's just an n by n matrix. So it's theta n squared. This is kind of bad news. That can be a lot if your graph has millions of vertices. So the good news is time to query if an edge exists. This is theta 1. This is constant time, right? You just V3 to V4, you just go to the cell in the matrix, check if it's 1 or 0, you're done. So this is good news. So let's look now at another. Well, any questions about the matrix representation? Okay, so let's look at the adjacency list representation. Here I have n linked lists. And the list of a vertex U holds all V such that UV is an edge. Okay, so all its neighbors V. So, okay, that's the definition of the list. Let's just see the example here with the directed graph. We'll look at our favorite example here. So I'll have a list for V1, and that list will contain everything going out of V1. That's just V2. And V2 will contain anything going out of V2, which is just V3. V3 contains V1, and V4 contains V3. In case of a undirected graph, we'll have to put a little bit more. So V1, its neighbors are V2 and V3. For V2, its neighbors are V1 and V3. For V3, its neighbors are V1, V2, V4. And for V4, its neighbors are V3. Plug this thing in. How many of you have had lectures end early because the professor's iPad or something ran out of battery? That's just good for me to know. Hasn't happened to me yet, but there's going to be a first time, I'm sure. Maybe even today. We're at 9%. So, but plugged in. So let's hope. See, we just went up to 10%. Okay, so jokes aside, here you see now the linked list, the adjacency list representation for the undirected graph. What is the space of this list? There's kind of a loose bound, and there's a tight bound. So the loose bound says, well, look, there's n lists, right? N lists. And how many vertices can one list hold? What's the most neighbors that a vertex can have? N. So n times n equals to O(n) squared. But this is not a good bound. I just want to show you this so that you know that you could do it this way, but there's a better way to do it. So the tight bound is actually a theta bound. So it's with a big O bound, that's what I mean by loose bound. Like, okay, I gave an upper bound that it's n squared, but I didn't show that it has to be n squared. There's sometimes it's going to be less. The theta is going to be a tight bound, meaning it's going to be exactly asymptotically exactly number of elements you'll see. So first thing is that there are n lists. Even if there are no edges, just n empty lists, you still got to store them. Like even if it's just a null pointer or something like this, for every linked list, or just some kind of variable that says, well, this is an empty list. So you need n in there. Now, how many elements are in the list? So this is what we want to put in here. Let's look at the directed example. Before we had our loose analysis said for every list we have at most n. But now let's instead look at all the lists together. Let's see if we can somehow argue on the number of elements in all the lists together. The way I'll do this, I'll say, look, take an edge, V1 to V2. Where does this edge show up in your list, in your lists? Well, it shows up in here, right? That's what this guy corresponds to. And that's it. It doesn't show up anywhere else. So every edge gives you exactly one element in these linked lists. V2 to V3 shows up here. V4 to V3 shows up here. And V3 to V1 shows up here. The number of elements in that list, in those lists together, is M. Each edge leads to one element in the lists. This is for the directed case. And what about the undirected case? So let's see the undirected case. The edge V2, V3. Well, it shows up as a neighbor of V2 here and shows up as a neighbor of V3 here. In the undirected case, it shows up twice. So in each edge leads to two elements in the lists for the undirected case. But the result is the same. Like if you put a 2 here, that doesn't change the theta. Doesn't change the theta. Okay, it's just a constant in front of m. Okay. So this is the space bound. It's theta n plus m. And this is the good news. We already talked about how to compare the space here and the space here. You can think about sparse and dense graphs. In the sparse graph, so let's say, yeah, sparse graphs. Base, we use matrix, or we use list. So in a sparse graph, the matrix has space theta n squared. Let's just end, but the list, now let's in the list convert this into what happens in a sparse graph. M, so theta n plus m, m is big O of n, right? That's what the sparse graph means. You put that together and you get big O of n, big O of n. So the list takes big O of n. In a dense graph, the matrix takes n squared, but the list takes theta plus n plus m. M is theta n squared. So that gives us theta n plus n squared, which is theta n squared. So the space in the sparse graph, is much better in the adjacency list. In the dense case, now it looks like they're equal and they are asymptotically, but this is the case where you as a programmer, you would look then under the cover and see what would be the constants involved in this theta n squared. For a matrix, you really just have n squared bits, right? So really the space used is n squared bits. No, without big theta, without asymptotic, without any hidden constant, just n squared bits. Here, you would use n squared, theta n squared space, but now what are you storing? So each of these guys is an integer probably, so that's like 4 or 8 bytes. And then this you want to store like a linked list. So you have pointers. A pointer is 8 bytes, 16 bytes, 64 bytes. Well, depends on your system. So really it's n squared, but then it's lots of bytes for each of those elements. Whereas in the matrix, we had just 1 bit. So you do see, if your graph is dense, you want to use a matrix. The bad news about a list is the query time. So what if I ask you, is there an edge from V3, or let's say from V2 to V4? Here, is there an edge between V2 and V4? Well, I got to go to V2 and go through this list until I find V4 or until I get that it doesn't exist. So it's not constant time. I have to go through this list. How long is that list? Well, in this example, you can't quite see it, But what if you have the graph that's like this? What if you have a graph there? This is V1. This is V2, V2. Then you have V3, V4, V5. These are all edges going out. And maybe you have V6 here, but otherwise you have V7, V8. Let's say it's like this. So then you have your V1 list is very long. It contains all the vertices except V6. It contains V2, V3, V4, V5, V6, not V6, sorry, V7, V8. So if you're going to ask, is there an edge from V1 to V6? Let me be more precise. So these are V3, and this is V4. So from V1, I can go to V2, V3, V4, V5, V2, V3, V4, V5, V7, V8. So if you ask me if there's an edge from V1 to V6, I have to go to V1's list and then go through all of this until I find that V6 is missing. So the query is order n time, because this, like in this example, you have this vertex that is highly connected and has n minus 2 neighbors. So its linked list is order n. So that's bad news for the adjacency list representation. Okay, now that's it for a presentation. Let's talk about algorithms, and we're going to look at something called depth first search. We're going to spend, like a book, I think, spends the whole chapter talking about depth first search. It's really a powerful application, algorithm behind many applications. But we'll start with a simpler problem, which is the reachability problem. Given, let's put this problem. Given a vertex V, return array called visited such that visited of U equals to true if and only if U can be reached from V. And what I mean about reached is probably what you intuitively would think, that U is reachable from V if there exists a path from from V to U. And I use this squiggly line, we'll use it more. We'll use that squiggly line to indicate a path from V to U. And now let's say you have the graph G as an adjacency list. So I'll give you an algorithm that I claim is going to solve the problem. It's called explore. Takes the graph G and a starting vertex V. Okay. We assume visited is initialized to false. So by default, visit is false unless we change it to true. So as soon as we explore V, we visit it as the first thing, and we set that to true. So we take all the edges going out of V. V to U is an edge. So for each edge, V to U, we check if U is not visited, then we explore it. So we don't want to explore something that's visited, but if it's not, then we explore it. So that's our algorithm, and I claim that when the algorithm terminates, your visited, it's going to have solved the problem that we set out, which is to have this visited array determine if you. Now, you think we'll get into the running time, but we'll often see this kind of loop. And this works really well with an adjacency list because we're not querying whether a certain edge exists. This is really, we just go through every element of the linked list of V. That's what this is doing. So this is just becomes just constant time per edge in this, if we query it like this. Let me walk through an example that I'll take from the book. Then you can cross-check your notes. You can, let's assume that the ordering of the vertices, assume vertices are ordered alphabetically. So in this example, you see they're called A, B, C, and so on. So that's going to make it easy for us to know their order. And let's do an explore from A. All right, so first thing we do when we explore A, we set it to be visited. So we put true. And I'll put a 1 here to indicate that this is our first recursive call. Now, we're going to look at all the neighbors of A. That's going to be B, C, D. And remember, we're going to assume that they're all written down in an alphabetical order. So the first one we'll check is B. And we'll check if B is visited. So no, it hasn't been visited. So we explore B. When we explore B, the first thing we do is we set it to be visited. And this is the second call to explore. Now we look at the neighbors of B. So what are the neighbors of B? A, E, F. A, we're going to check, and we're going to see that it has been visited. It's true. And so we don't look at A. Then we look at E, and E has not been visited, so we explore E. This becomes true, and that's our third visit. When we're exploring E, we're going to look at its neighbors. B has already been visited. I, J have not. So next one in order is I. We're going to explore I. That's going to be our fourth thing. Notice as we were doing this, we were really exploring along an edge. So we were exploring A, and then we went to B. We took this edge, and from B, we took the edge to E, and we took the edge to I. These edges are going to have special meaning, as we'll see next lecture. Any questions? Yeah. There's no terminating condition for the loop. That's a good, I mean, for the algorithm or for the loop, because for the loop, you just explore all the edges, and then, you know, you're done with the for loop, and then you're done with the call. So for the algorithm, when you start with visited A, eventually what happens is you'll go to visit a node. It will happen soon. We didn't get to J. When we get to J, all its neighbors would have been visited. So we would have not started any recursive call and we would have just ended the function. And eventually, all the explorers would have finished because we would have visited everything. So we'll start next time with this example. I think it will clear things up.